52, 55. Wow. All right. Let's see. Say again? Yeah. 52. Ah. All right. 52. Each channel of a stereo receiver is capable of an average power output of 100 watts into an 8 ohm loudspeaker. What are the RMS voltage and RMS current fed to the speaker? At the maximum power of 100 watts, and at 1 watt when the volume is turned down. Well, we know two things. We know power and we know resistance. So, $100 watts into an 8 ohm. What are the formulas for power? Equals, what was that now? I squared R over 2. Okay. Looks good to me. That will give us a peak current, right? But it didn't ask for peak current. It asked for what? Your RMS current. And what's RMS current? Square root of 2. So I naught over the square root of 2 times I naught over the square root of 2 is equal to IRMS times IRMS, right? So I naught squared over 2 equals IRMS squared. So this is actually equal to IRMS squared times R equals P. Everybody with me? Well, 100 watts equals IRMS squared times 8 ohms. That gives us IRMS equals, forgive me if I skip a couple of steps, principal square root of 100 divided by 8, which is what? 12.5. .5 amps. That's your RMS current. What else do they want to know? Okay. Your power, 100 watts, is equal to your RMS voltage times your RMS current. So 100 watts divided by 3.5 amps would give you your RMS voltage. Is that what it worked out to? Did anybody get a different answer? Boom. Okay, that. Now, that's part A. Now for part B, power is reduced from 100 watts down to 1.0 watts. So let's just repeat. 1.0 watts equals IRMS squared times 8 ohms. 1 over 8 to the square root equals your RMS current, which is, say again, 0.35 amps, or 350 milliamps. Did anybody get anything different? Did at least somebody else get the same thing? Okay. And 1 watt is equal to 0.35 amps times VRMS, which goes to 1.0 divided by 0.35, gives you how many volts RMS? 2.86. So good? All right. Anybody that turned in homework want to take theirs back and change any of it? No? Okay. What was the other one? 55. Oh, that cursed drift velocity. I do not remember the formula. Believe it or not, I don't memorize 90% of the stuff we do in this class. The point of learning the material is not memorizing the formulas, the equations. The point is learning how to use them, how they work. What does the math actually mean? What does it say? How do you translate it? You can always look up the formulas, hence the index cards. Now, start by looking up the formula for a drift current, for the drift velocity of those electrons. Drift velocity is equal to current divided by the number density of your electrons times the charge of an electron times the area. Yeah, we will. First, we've got to figure out how many electrons are in that volume. And it's copper wire. So didn't we already do that? No. Per cubic meter, right? Let's do that. First, call it out to me again, Dalton. That's our N. And we know E is 1.6022 times 10 to the minus 19 coulombs per electron. And our area, what's our area? We have a 0.65 millimeter diameter. So area is equal to pi times r squared is equal to pi times, what was the 0.65 times 10 to the minus 3 meters squared. It's the diameter divided by 2 squared would be divided by 4. So if we're dividing by this, we're going pi times 0.65 times 10 to the minus 3 squared divided by 4, which goes back up on top. And our current is 2.7 microamps, right? So that's times 2.7 times 10 to the minus 6 amps. Because division is multiplication by a reciprocal. If I am dividing A by B over C, that's the same thing as A times C over B. Division is multiplication by a reciprocal. Multiplication is simply addition, successive additions. 3 times 5 is 5 plus 5 3 times. Subtraction is merely the addition of a negative. So at the end of the day, all arithmetic boils down to addition. Okay, so that's our equation that we need to solve. Somebody with a calculator. In fact, everybody with a calculator. Somebody call out an answer. Yeah, 6.045, so that would be 0.05, whatever. 6. There we go. 6 times 10 to the minus 10 meters per second. What's the, how many of you are familiar with atomic scales? 10 to the minus 10 meters is roughly the diameter of an atom. That means the mean drift velocity of the electrons in that wire is roughly the distance of 1 atom per second. Nope. Any more questions from the homework? Or I guess not. 2, 3, 4, 5, 6, 7, 8. Two of you still holding out on me. Who's not turned in yet? Oh, yeah, got it. And everybody signed in? Yep. All right. Who's ready to start on chapter 19 now? Ready as you will be? Okay. Sometimes that's just good enough, ain't it? All right. Oh, I've got stuff here to hand back to y'all. Any of you anxious to get it back right away? Okay. We've already covered batteries and cells, right? Y'all can tell me the difference between a cell and a battery? Cyrus, you're smirking. That's a quick call on me. What's the difference between a cell and a battery? Exactly. In fact, that is literally what the word means. It's a group. Think about battery park. It's not because they make little Energizer bunnies there. It's because they lined up a bank of cannon in the ramparts and fended off the British ships. A battery is a pile or a group. And in the case of electricity, it's a group of cells. What is the output of a battery? Or a generator? Or anything that converts one form of energy into electrical energy? Whether it's chemical, mechanical. Huh? Well, yeah, it's DC. It could be AC, but in the case of batteries, and in the case of this chapter, we're going to stick to DC circuits. So we're talking about a battery. It could be a generator hooked up to a bridge rectifier. The DC just means it's always going in one direction. What is the output? Exactly. Voltage. And if you've studied electronics, you know they come up with something, this construct called a constant current source that you can put on your schematics. Well, you can build a constant current source if you build a very complicated circuit that will maintain an output current and change the voltage as needed to do so. But batteries generally are not constant current sources, they're constant voltage sources. Their output is always going to be a voltage. And we say constant voltage, even though they aren't really that. The voltage of a battery will vary, it will change, depending on the amount of current that's being drawn and on how much charge it has left, or how much life it has left in it. The output, just cover some vernacular for you. The output of the battery is called EMF. And in the book, it's generally going to be denoted with a script E to distinguish it from the uppercase Latin E, meaning the electric field. This has units of volts. Electromotive force. It's the force that pushes the electrons as they migrate down the wire, or a conductor. Now, they tell you in here to be careful not to confuse volts with voltage. Can someone tell me the difference? So you may be kind of not quite. You're on the right track. Voltage is what they call the EMF. Volts are the units associated with EMF or voltage. Okay? Yeah, it's absurd. It's a little bit bizarre. It can be confusing. It's just the way the vernacular evolved. We get a battery. We don't talk about the EMF rating of a battery. We talk about the voltage that it puts out. And that voltage is measured in volts. And it is the potential difference between the terminals of the battery. Now, Ohm's law. I think I saw all of y'all doing that on your tests as a means of remembering Ohm's law. You drew the circle. Okay. If you have a certain current flowing through a resistor, how much voltage will drop across that resistor? E equals I times R. So if you have a 1 amp flowing through 1 ohm, it's going to drop 1 volt across that resistor. What if you have, and how many of you have done that, have actually worked under your hood of your truck or car and measured the voltage on your battery? On your car battery. Your car battery is a 12-volt battery, right? Have you ever actually measured the voltage? Do this sometime. Get a voltmeter out, open the hood of your car. You don't have to unhook anything. Just lift the hood, put your voltmeter across the battery. It's probably going to measure something like 13.5 volts, 13.2 volts, something like that. But what happens when you hit the crank, when you hit the ignition, and it starts sucking down current? What happens to that terminal voltage then? It goes way down. Where does it go? Where does that voltage go? Because that's potential difference. It's there. Here's our schematic. There's your 12-volt source, which is actually 13.2 volts, terminal voltage. There's your terminal. There's your terminal. Here's your starter and your ignition switch. 13.2 volts. You measure, put your voltmeter here to here. You measure 13.2 volts. Close that switch, current starts flowing. That 13.2 volts drops down to what? I don't know, 10, 9 volts, 6 volts, whatever. Let's say 10 volts just for our purposes. Where did that extra 3.2 volts go? No, the 10 volts is across the starter. You're measuring that right there. You've got you're measuring the output from that battery. As soon as that starter kicks in, it starts drawing amps. I don't know, how many amps? 20? 10? How many amps does it take to turn over that big block engine in your truck? Let's pretend like 10 will do, because I'm making up these numbers here. These do not, if you're going to take your SAE certification, do not trust these numbers. Measure your own. Let's pretend like it's 10 amps. And you're right, they do sell these batteries with 300 cranking amps or whatever. 10 amps flowing through that solenoid is dropping 10 volts. What does that tell you about the resistance of that solenoid? One ohm. You've got 1 ohm of resistance. If you've got 10 amps flowing through it and you're dropping 10 volts across it, you've got 1 ohm. But that still begs the question, where did that other 3.2 volts go? 3.2 volts divided by 10 amps equals how many ohms? There are 320 milliohms of resistance somewhere. It has to be. Because when no current is flowing, you've got 13.2 volts. But as soon as 10 amps start flowing through that battery, because remember, all the electrons coming out here have to go through here and then have to come back here. So, somewhere there's 320 milliohms of resistance. Now, well, in point of fact, you are going to lose some to copper losses, but this is a big old fat honking 10 amp wire that's going from that battery to that starter. And the ground is the whole frame. So you're talking at the most micro ohms. But you're right, there would be some loss to the wire. The wire is not resistance free. It has some finite resistance and it will drop a little bit of voltage, but we're talking microvolts here at this point. What were you saying? Okay, what is core loss? Huh? Yeah, that's eddy currents in the core. Yeah, you laminate the core and you can minimize it. Yeah. That's you're on the right. You're closer to the right track than you might think. This is your battery. These terminals are all the access to that battery you have. But there is a phenomenon inside that battery, inside the chemistry or inside the solar panels or inside whatever mechanism is converting one form of energy into electrical. And that is, and I'm probably drawing it on the wrong terminal, but it's all series, so who cares? An internal resistance. Every battery has it. There is internal resistance in that battery, and the physics and the chemistry involved is way beyond the scope of this course. But as that battery ages, as it gets old, as it gets charged and discharged and recharged and redischarged over and over again, as it gets hot in the summer and cold in the winter and goes through freeze and heat thaw cycles, that internal resistance starts to grow, get bigger, and creep up. That's why when your battery finally gets so dead, so old that it won't hold it, it's no good anymore. It can be because this internal resistance just got to be too big. In this example, that R internal is right there. That is where that extra voltage goes when you start drawing a current out of your battery. take out those little 1.5 volt AA batteries, or D cells, or AAAs. You put your voltmeter across it. It may say 1.5 volts on the package. If you measure it, it's going to be more like 1.65 volts. Open terminal. And yeah, as the battery dies, the apparent internal resistance will increase. Now, what then, in this case, we talk about at 10 amps, we would talk about this 10 volts that appears at the terminals of the battery as the terminal voltage of the battery, which is basically the EMF of the battery minus the current times the internal resistance. That's the amount of voltage left at the terminals once it's under load. Now, let's I do want to spend a little bit of time on this. Let's look at resistors in series and in parallel, because some of you had to kind of dig way back deep into your brains for that electric circuit lab, figuring out how to analyze these compound circuits. And it is going to get worse before it gets better in this class, because we're also going to get to the point where we're analyzing circuits with multiple sources. And that's going to mean setting up and solving systems of equations simultaneously. Two equations, two unknowns, that sort of thing. So, let's start with, we put 3 resistors in series. R1, R2, and R3. They're all in series. That means that whatever current is flowing through one of them must be flowing through all of them. Right? So the voltage here is voltage here, and the voltage here, well, the total voltage applied to the circuit has to be equal to the sum of the voltages around the circuit. And even though I'm ignoring internal resistance here, I would point out to you that if I wanted to be technically precise, all I'd have to do is find that as my terminals, and we would have 2 resistors in series with the battery, and R1 would be the internal resistance. Okay, so I'm not gonna keep harping on internal resistance now that unless it comes up in a particular problem. But in general, the voltage applied has to equal the sum of the voltages all the way around the circuit. If we apply V, then V must equal V1 plus V2 plus V3. Right? That means it is equal to I times R1 plus I times R2 plus I times R3, which I can factor out that I is equal to R1 plus R2 plus R3, which is equal to I times the total resistance, or net resistance. Therefore, for resistors in series, simply the total resistance is simply the sum of the resistances. Not really very surprising, is it? All right, let's take a look at a different configuration. Now we have our voltage across these resistors in parallel. What is the voltage across R1? Say again? Same as the source voltage. Same voltage across R2 and the same voltage across R3. How much current is flowing through R1? Same here. I2 is equal to the source voltage divided by R2, and I3 is equal to the voltage divided by R3. Now this is Kirchhoff's current law. This was a statement of Kirchhoff's voltage law. The sum of the voltages around any closed loop must sum to 0. And if this is plus V, then that's the positive and that's the negative side of that resistor. That makes this the positive and the negative side of that resistor. At each resistor, the voltage is going down. So you start off at 12 volts, or you start off here at 0, you add 12 volts, and then you subtract this part, you subtract that part, you subtract that part, you wind up back at 0. Okay? Here, Kirchhoff's current law says that the total current coming into any node must equal the currents leaving that node. Here you have I2, the total current minus the I1 entering this node. And you have I2 leaving here, so this must be I total minus I1 minus I2. And that is equal to I3. Here you've got I3, which is I total minus I1 minus I2 coming into this node here, gaining I2 here. So the total currents coming into this node must equal the total current leaving that node, which would be I total minus I1 minus I2 plus I2. So this becomes I total minus I1. Here it regains I1 to become I total I really can write better than that. I total minus I1 plus I1, which equals I total again, back into the battery. The total current flowing into any node must equal the currents leaving that node, or vice versa. That is Kirchhoff's current law. So, what we have here is I1 plus I2 plus I3 must equal I total. Right? Well, what is the I total? The total current flowing through that circuit is the total source voltage divided by the total resistance of the total combined resistance of the circuit. That's equal to I1, which is the source voltage divided by R1, plus I2, which is the source voltage divided by R2, plus I3, which is the source voltage divided by R3. Is that looking familiar to anyone? What happens when we divide through by the voltage? We get 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ad infinitum. The reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. Or, if you take the reciprocal of both sides, you get the reciprocal of 1 over RT is RT, and that becomes reciprocal of that, which is 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3. The total resistance of resistors in parallel is the reciprocal of the sum of the reciprocals. Now, I've already told you about Kirchhoff's rules, voltage law and current law. So we got a few minutes. Let's look at some examples of how you would use these rules for series and parallel combinations of resistors together. I want to start by, before we go into it too much further, I want to start by making a point with y'all. How many of you have a calculator with a reciprocal button with a reciprocal key on it? Reciprocal key will either be labeled 1 over x or x to the minus 1. Okay. You have no doubt, if you have studied electronics, you've no doubt been told that if you have a special case of only 2 resistors in parallel, you have this, you can combine by multiplying this by R2 over R2, which which is just multiplying by 1, so you don't change anything. This one you multiply by R1 over R1, which is just multiplying by 1, so it doesn't change anything. So this becomes 1 over R1 over R1 R2 plus R2 plus R1 over R2, R1, R2, which equals 1 over R2 plus R1 over R2, R1, which equals R2, R1 over R2 plus R1. And they probably sold you that this was a simpler way to calculate two resistors in parallel. Point something out. First of all, not only is this limited to a very specific case of just two resistors in parallel, if you want to calculate your total resistance in this way, you have to key in the value of R2 times the value of R1 divided by, open parentheses, the value of R2 plus the value of R1, close parentheses, equal. If you want to calculate it this way, then what you have to actually key in is the value of R1 reciprocal plus the value of R2 reciprocal equals reciprocal, and you're done. This simplification actually takes longer to calculate on your calculator than just doing the reciprocal of the sum of the reciprocals. So, I just wanted to point that out to you. Now, for those of you with the fancy palm-top computers with their own programming languages and all the extra graphing functions and whatnot, I don't know how you would have to, I don't know which would be easier on yours. But on a normal calculator with a reciprocal key, number reciprocal plus number reciprocal equals reciprocal, and you're done. Now, let's how would you analyze the net total resistance of that circuit? Dustin, where would you start? What's the first thing you would do? Somebody else, chime in. Say again. Which one? Okay. Here's the way you do this. You start by going to the farthest point away from the source that you can go. You've got these two resistors in parallel. Let's number them. There are 7 of them in parallel. So the first thing you're going to do is you're going to calculate R5 in parallel with R6. And that, let me start over here. R5 in parallel with R6 becomes a single resistance value. So your circuit just got simplified to that. Well, now when you come to the farthest point away from the source, you've got 3 resistances in series. I'm sorry, not 5, 7. And that gives you this single equivalent resistance value right here. Now you've got this, which I'm just going to call RM, or medium or middle or whatever, somewhere in the middle of the calculation. Now you've got RM in parallel with R3 in parallel with R2. So that would give you R net is equal to the reciprocal of 1 over Rm plus 1 over R3 plus 1 over R2. And that gives you R sub n. Which replaces all of that with R sub n. Now we've got R1 plus Rn, and that gives you your total resistance. The trick is to start at the farthest point from the source, and then just take them in groups so that you can combine them into equivalents, and just keep working your way back to the source. And if on a problem you also had an internal resistance, it would just be added in series with your load resistance. Any questions? Yeah. Right. Yeah, if you had an internal, if you had a problem where you were dealing with an internal resistance, it would just be in series with that. It would just become your voltage drop internal to the battery as opposed to the voltage across the rest of the load. But according to Kirchhoff's voltage laws, that voltage can't just disappear. It goes somewhere. It has to be accounted for. So if you start off with 13 volts coming out of that, 13 volts of EMF coming out of that battery, before current starts to flow, then you have to account for all of 13 of those volts once the current starts to flow. And basically, it's any that is not dropped across load resistors somewhere outside in the circuit has to be internal, has to be dropping internally across an internal resistance. Kirchhoff's current law is the other big important one. In fact, I think the lab this week is about Kirchhoff's rules. So, same as last week, you have your own software for simulating circuits. Try to say that 3 times fast. Your own circuit simulating software. Be sure to bring it. If you don't, you're going to be stuck using some of the state-of-the-art 1980s computer technology.